Hello SGD Sacred Geometry Decoded. This will be part 12 in the series about understanding the Great Pyramid, the pyramids of Egypt, the geometry, astronomy, arithmetic and music contained therein. This one will be, well, geometry, geo as in geology, earth, metry, measure. This will be about the Great Pyramid and the Great Pyramid as a model of the earth. Last couple of episodes, I'll just quickly, so we're talking about the great architect, the geometry of especially the Giza pyramids. Previous to that, I showed how the red, the bent, the Maidum pyramid and have these same aspects and the same geometry proportions, actually link them all together in a very beautiful way. And so the geometry of the Great Pyramid is a scale model of the Earth and the Moon, showing those proportions between them. And so all this, but also all the measures connected, we'll come back to this because the idealized measures is found in the Salamis stone, but also which also contains Egyptian. So the base length of the Salamis stone is the square root of 5 Egyptian royal cubits, which is so important to the golden number. But these particular measures and numbers will come back, especially in astronomy, in very lovely ways. So pointed out that the moon itself, this diagram, the geometry of the Great Pyramid, or the Maidum pyramid, or the capstone found next to the red pyramid, has the geometry contained therein actually also defines the barycenter of the point at which the moon orbits the Earth. And how, for instance, these numbers, I'll come back to these because it's all in the geometry, it's in the architecture throughout time, still being used now. But how these aspects and all the measures, the proportions, the geometry of this all connects. And so also gods of weights and measure, Thoth, Sheshet, Hermes, Mercury, Nuar, Thuzi, plumb lines, compass and square, weights and measures, astronomy, architecture, knowledge, maths, geometry, chemistry. These are the and information contained therein. So this was in the last one. So again, how the pyramids themselves, not just the Great Pyramid, but how they interrelate with one another, like physically on the floor in relation to their proportions to one another, but also how with the same geometry we can find even the ratios of distance between the planets, and taking Bode's law to and the next level really. So this was in the previous episode. It all now I could extend this, I will in the future, but just to begin with, I was just talking about the inner planets. The same method also describes the position of the asteroid belt or Ceres. Also Saturn, Jupiter will come in very nicely in there as well. But for the moment, also the distance from the Earth to the Moon being just a shifted decimal place. And yes, so the same, well, Sun, Mercury, Venus, Earth, Mars, the distance from the Earth to the Moon, and time will be an important feature because the sidereal and the synodic month are also embedded in here. So is the lunar year, and we'll come again back to these because that's embedded in the different systems of measure. The imperial or the English system, the meter, and the royal cubit are linked beautifully through the measures, and also the measures of time and the measures of distance and the measures of size of astronomical bodies and, well, the human body as well. So the great architect geometry, the tools of geometry. Now the Great Pyramid is a model of the Earth. Geometry. Okay, so geometry. Now an important feature about the pyramid is that the pyramid sits on two they're often overlooked, but what we have is the paving stones or the socle, and at the corners we have something called the sockets. Now, for instance, the socle, where you can see the paving stones where the pyramids are built on. Now, it's often said that these are perfectly laid. No, they're not perfectly level. They vary by about an inch, but this slope in itself, this margin of error, as with so many other, and the margin of error contains the next level of extraordinary information. But this 1 inch difference will add an inch to the height of the pyramid essentially. One side of the paving stones is an inch shorter than the others, which adds to the height. but also just from a Google Earth snapshot, you can get an idea of the height of the paving stones or the socle, 55 centimeters as a general rule, a very accurate general rule. So 55 centimeters for socle for paving stones will add to the height of the pyramid. At each corner we have something called the sockets. Now there you get an idea of it, but many surveys have been done of this. Do I have a... Okay, so there's a J.H. Cole survey which describes a pyramid in itself, including the slight variations. This is part Petrie, Piazzi, Smythe, Royal Engineers also measured the sockets, these blocks at the corner. So along this line, that square there is the pyramid. Okay, yep, so there we see the base of the pyramid, and there we see the sockets. Now this even has a plan of sockets magnified. So they look larger there than what they are. They basically add roughly 2 feet or 4 feet in total to the edge length. So given that the pyramid is basically 756 feet long, these are slightly over. So those are the sockets at the corner. They add on each side, so 2 foot on this side, 2 foot on that side, roughly speaking. But the sockets add length to the base. The socle adds height to the top. And to scale the pyramid to the size of the Earth, you need to include these things. Now, there's that squaring the circle in the Great Pyramid, which is also shows a nice relationship of the Earth to the Moon. Now, this is the image of, or the number given so often to describe the relationship of the Great Pyramid to the size of the Earth, and the number is 1 to 43,200. This is correct, but there is a much better way to look at that. But first, we'll examine this 43,200. So to begin with, what you have to do is you have to get a bird's eye view and measure the perimeter of the pyramid. If you multiply that by 43,200, you get the equatorial circumference of the Earth at the equator. An important feature is to note that the equatorial circumference is more than the polar circumference because the Earth is flattened ever so slightly at the top. And the pyramid describes this flattening. This is one of the extraordinary things. Now, however you do it, this is described therein. So if you look at the socket plans, you can get the measurements from there. We add them all to, so 9,130.55 inches. This was all done in inches. If you add them all together, we get 36,518.52 inches. 36 is a very nice connection to 365, but that turns out to be 3,043.21 feet, or 0.9275, etc. kilometers. That's the perimeter of the pyramid, including the sockets. Now, especially the southwest one, there's an issue there, but just to stick with this for the moment, we'll come back to this later. So, if we divide the equatorial circumference by 43,200, we get 0.9726643 kilometers. The perimeter of the Great Pyramid, essential to include the sockets there, is 0.927504. So very, very close. Just under a meter. Very, very close from what we would hope. So this is a level of precision unrivaled. Sorry, that circumference. Typo there, but you get the point. All right, so very, very close, very, very accurate. And then we look at the polar radius. So from the equator to the poles, which is less than the equatorial diameter or equatorial radius, but so the Earth polar radius is 6,356.752 kilometers. Each measure varies because it's very tricky to get exact measures because there's so many aspects. Do you measure from sea level, from the top of the highest mountain, etc. But if we divide that by 43,200, we get 482.766 feet, or 147.147 meters. That's the number we would hope to get. The height of the Great Pyramid, including the socle or the paving stones, times 43 should be the polar radius of the Earth. Now, the height of a pyramid, it can be vary ever so slightly, again depending on what measurement, but at 280 Egyptian royal cubits, which is pi over 6 meters, would be 146.604 meters, or 480.996 feet. This corresponds to Petrie's and others by 0.4 feet. But we need to add the height of a socle, which is the paving stones, 55 centimeters, or it should be a dot, not a 1.80446 feet. Add them together, we get 482.8 feet, or 147.15765 meters. That's the height of a pyramid, including the socle or the paving stones. And so the number we want, compared to the number we get, again, very, very close. 482.766 feet would be the ideal number we're looking for, and we get 482.8 feet. And because of the inch discrepancy between how to measure it exactly, again, very, very close, very, very close. So the pyramid really, really like rivaling the most modern satellite measures. So if you include the socle and the sockets in the base length and the height, or the perimeter, base perimeter, and the height of the 43,200 scale, works to an accuracy unrivaled until the modern satellite age. However, and this is a big thing, this is what it's describing. It describes an Earth that looks like this. It has the equatorial circumference and the polar radius. But the solution to this problem is in the image itself, because this shows a pyramid as it is. It's a 3D object. We're standing at the corner of a pyramid. So this image itself actually gives you the solution. So neither the Great Pyramid nor the globe, the Earth, is two-dimensional. The 43,200 method relies on one two-dimensional view of the pyramid, the perimeter, and then the height of it, which is another two-dimensional view. So you need two separate two-dimensional views of the pyramid to get a half Earth, or in a half globe. But the solution is there, because that's the pyramid. It's a three-dimensional object. If you stand at the corner, you can see the pyramid is all pyramids are three-dimensional. The Great Pyramid is three-dimensional. You need to think about it that way, because extra dimensions will add dimensions of knowledge and information contained therein. So the Great Pyramid is a scale model of the Earth at a ratio of 1 to 86,400. And because if we stand at the corner of a Great Pyramid, we see the height, and we see the maximum visible base length, what you'll see of a pyramid. We see all the view that we need is right here, and it's at 86,400. So instead of multiplying the perimeter by 43,200, we multiply the maximum visible base length. Stand at the corner, you'll only ever see two sides of a pyramid. If you multiply that by 86,400, we get the equatorial circumference of the Earth. You can just use the same measures of the 43,200 method. We just divide them by 2 and then multiply by 86,400. Now we have the equatorial circumference of the Earth. But as a bonus, we have the rotational speed of the Earth, including the sockets. The maximum visible base length of the Great Pyramid is the equatorial circumference divided by 86,400, 86,400 seconds per day. Therefore, we have the rotational speed of the Earth per second. We're going to go into this again more in the future, because this is really about the meter of a pendulum, the cubit, and the English foot. But a 1 meter pendulum should not be swung at more than 30 degrees. This is a well-established rule. The Great Pyramid itself is ever so slightly less than 30 degrees north of the equator, but a 1 meter pendulum creates 1 second, and that is 1 Egyptian royal cubit per meter per second. And the cubit connect, and so they will to the English foot also. So now we have the rotational speed of the Earth per second, as in 86,400 seconds per day. The maximum visible base of a three-dimensional pyramid, including the sockets, multiplied by 86,400. we get the equatorial circumference of the Earth with the same precision. Now, this will link, again, 1 second of time with the Egyptian royal cubit with meters and the measure of man, including the imperial measures, and we'll touch on that. So now let's look at the height of a pyramid. We can use exactly the same number we used already for the 43,200 method, but instead we multiply it by 86,400. Now we get the polar diameter of the Earth. Not the polar radius, now we have the whole Earth. So at 43,200, that's what you get. If you multiply it by 86,400, this is what you get. The pyramid is scaled to the Earth at 86,400. That's important because back to the ideal measures of a man. So the English system, 4 cubits being a definition, like even shown in Vitruvian Man, 4 cubits should be your height and should be the fingertip to fingertip, which would be equal to 6 feet. But okay, let's remember this. Now, the English system, they would define, so inches or thumbs and then digits, and then barleycorn, and then barleycorn are divided into poppy seeds. So 4 poppy seeds is 1 barleycorn, 3 barleycorn is an inch. But the ideal human body using the English system is 864 poppy seeds. Now this will come back to that the actual Vitruvian Man is closer to 6.9 feet, and that 6.87 or 6.9 English feet is equal to 4 Egyptian royal cubits. So the ideal Egyptian man, being 4 royal Egyptian cubits high, is described by this particular system in Vitruvian Man. Now, 6 English feet, so 1 meter plus 1 Egyptian royal cubit of pi over 6 meters plus 1 English foot equals 5.9987 feet. This was put together now by, so again, the meter, the Egyptian royal cubit, the second, but also the foot. But 1 meter plus 1 Egyptian royal cubit equals 4.999 feet. However, the difference between that, so what you have, this was Alan Green noted this relationship between the meter, the Egyptian royal cubit, and the English foot, and that is ever so slightly short. That's 0.396 millimeters difference. Now what that means is if you were to insert 1 human hair in between each of these 3, it would equal 6 feet precisely. That's how precise it is. So the number might not look like it matches, but in all but in laboratory conditions, this is 6 feet, and this is, which brings us back to 864 poppy seeds. Now, even this margin of error is repeated in other places and very interesting connections. But so the meter, the Royal Egyptian, and the cubit, which also link together via the 1 meter pendulum, creating 1 second, creating 1 Egyptian Royal cubit, as in 86,400 seconds per day, which is the ratio that we need to find from the Great Pyramid to connect to the Earth. Now, there's a lot more information in regards to this, but 86,400 or 864, man is a measure of all things. Back to astronomy. Now, the metric and the imperial system, and the second, which defines the Egyptian royal cubit, the meter, the second, the cubit, and the foot, well, there are 86,400 seconds per day. You multiply the Great Pyramid height by that, you get the diameter, polar diameter of the Earth, multiply the half base of the Great Pyramid by 86,400, you get the equatorial circumference of the Earth. Thus you've described the whole Earth, and you've linked it with the meter and the cubit and the second. Now the imperial system, as in the meter plus the cubit plus the foot, Egyptian royal cubit, plus the English foot equals the man of 6 feet. Well, in the imperial system, the mean diameter, I should say the mean diameter, but still very above 99%, 99.9%. 864,000 miles is the mean diameter of the Sun. The average diameter of Jupiter is 1/10 of that, 86,400 miles. 86,400 miles in Jupiter, 86,400 seconds per day. Multiply the pyramid by 86,400, you get the Earth in itself. Now that same number, 86,400, that's the orbital speed of the Moon in kilometers per day. Time the metric system. So at 1 kilometer per second, the average is 1.022 kilometers because it changes slightly, but it will be traveling at precisely this speed at certain points in time. Just like the elliptical orbits, all these things slightly vary, but if you were to say this, you would be 100% correct for part of the time. Now, it just so happens that the orbital speed of Saturn is 864,000 kilometers per day. 864,000 miles, the Sun. 864,000 kilometers per day, Saturn. That's 10 kilometers per second. Now, the distance from the Sun to the Earth is 1 astronomical unit. The distance from the Sun to Saturn is 10 astronomical units. There's some lovely stuff going on in regards to this 1 to 10, 1 to 100, 1 to 1,000. So 86,400, 864,000, or 864. This links these systems of measure, as the English links to the Egyptian royal cubit via man is the measure of all things. The meter of the Egyptian royal cubit plus the foot describes a 6-foot man using the English system. The meter and the cubit come together via the second. Now, 1 Egyptian royal cubit is E minus 1 feet within a human hair. Again, that's how precise these are. So seconds, cubits, meters, 86,400 seconds per day. The astronomy already seen linked through the pyramid, and that same number which defines the pyramid, which is well, it's all over the ancient world. Let's put it that way. But yes, 86,400. Once you accept that, once you put the 43,200 to the side, and again we look at the measures of a pyramid, a whole other set of extraordinary information will emerge from it. Now, also might be worth noting, precessional information, 72, 216 are in there as well. Well, a whole bunch of so man is a measure of all things. Time and distance, length, and even this will come together through systems of weight. Modern systems, but also ancient systems. And the key to that is the pendulum, these units of measure, and the ancient architecture, which is repeated not just in the Great Pyramid. The Great Pyramid links to basically all the other major pyramids of Egypt, and the same geometry can be found across the ancient world. Stone circles, the megalithic sites in Karnak, Greco-Roman temples, ancient Hindu temples as well, and also, funnily enough, in Mayan temples as well, through these numbers, through these same small group of weights and measures. For measures especially, man is a measure of all things, and the Great Pyramid is a scale model of the Earth at 86,400, as in seconds per day, meters, cubits, feet. It all links. A lot more to come still, but pyramid astronomy, geometry, arithmetic, and music, weights and measures, Thoth, Sheshet, Hermes, Nuafuzi, pendulum, square and compass. It can be measured, and it's there. With that, have a good one. More to come.